All right. Hello, everyone. Welcome back. Today we will be talking about digital terrain and 3D maps. So, the Earth is not flat, as I hope all of you already were aware. We have spent this entire semester talking about how maps and GIS are representations of the real world, but we have yet to talk about how the terrain and the surface of the Earth. The Earth isn't flat. All of the maps, imagery, and coordinates discussed so far have dealt with two-dimensional images of either the surface or the developed or natural features on the land. We haven't yet described how the landscape can be modeled with geospatial technology. When we're examining landforms on Earth's surface, we will have to assign an elevation to each location. In terms of coordinates, each XY pair will now have a Z value that will indicate that location's elevation. These elevations have to be measured relative to something. When a point has an elevation of 900 feet, this indicates that it is 900 feet above something, and that something represents a baseline or vertical datum. That is the 0 point for elevation measurements. Some maps of landforms indicate that the vertical datum is taken as mean sea level, represented by the National Vertical Datum of 1929. When the vertical datum is used in an elevation value on the map indicates 1,000 feet, that number can read as 1,000 feet above mean sea level. Much geospatial data in North America utilizes the North American Vertical Datum of 1988, NAVD88, as the origin point for elevations. In 2022, the U.S., as part of its reference system modernization, will replace its North American datum of 1983 with a new Northern American Terrestrial Reference Frame, or NATRF 2022, creating 1.3 to 1.5 meter horizontal coordinate system, or coordinate differences at the Canadian-US border with respect to Canada's NAD 83. A common method of modeling the landscape is through the use of contour lines, imagery lines drawn on the map that join points of equal elevation. A particular elevation on the surface is represented by a contour line drawn on the map. However, because elevation is really a continuously variable phenomenon, it's often difficult to represent every change in elevation, such as from 8 feet of elevation to 10 feet of elevation, without overloading the map to the point of uselessness with contour lines. Thus, these contour lines are drawn a certain elevation distance apart, say a new contour line for every 50 feet of elevation. Map shows contour lines at a 20-foot interval on a landscape, outlining the creek knobs. The map shows green along the banks of the creek, denoting vegetation. This elevation or vertical difference between contour lines is called the contour interval, and is set up according to the constraints of the map and the area being measured. In general, a wider contour interval is selected when mapping more mountainous terrain, and a narrower contour interval is used when mapping flatter terrain. A widely used method of representing terrain features using contour lines is a topographic map, which is a printed paper map designed to show the topography of the land and the features on it. A U.S. topographic mapping program that ran from 1945 to 1992 produced topographic maps that were published by the USGS at a variety of map scales. A common topographic map was a 1 to 24,000 quadrangle, also referred to as a 7.5 minute topographic map, insofar as it displays an area covering 7.5 minutes of latitude by 7.5 minutes of longitude. Topographic maps were also available in smaller map scales, such as 1 to 100,000 and 1 to 2 million. The original USGS topographic maps were made up until 1992 and have since been replaced by the digital versions. Like the old topographic map, the US topos are delivered in 7.5-minute quad sections, but they are in GeoPDF file format. Why? Map production has changed as well. It used to take a very long time to produce a topographic map. Now the USGS produces over 100 US topographic maps per day. The US topographic maps cover the entire country and are on a 3-year revision cycle. In addition, the USGS now has over 175,000 of the original topographic maps in digital format, which are free to download. A digital elevation model, or DEM, is a specific type of model of the terrain and landscape that is based on regularly spaced point data of elevations, but is normally converted to a raster grid representation. In grid format, the elevation values are represented by the grid cell value, and the grid resolution represents the size of the cell being measured. Thus, we measure DEM resolution in much the same way that we measure the resolution of a remotely sensed image. If a DEM has a 30-meter resolution, then each of the DEM's raster grid cells is set up at 30 meters in size. A common source of terrain data is the Shuttle Radar Topography mission, which originated as a part of a mission of the Space Shuttle Endeavour in February 2000. For 11 days, Endeavour used a special radar system to map Earth's terrain and topographic features from orbit, and the result was a highly accurate digital elevation model. At the mission's close, roughly 80% of Earth had been examined in models as 90 meters DEMs. 30-meter DEM data was also available for the United States. SRTM is updated by NASA. In geospatial technology, terrain and landscape features can be represented by more than just contour lines on a map. Digital terrain model is a model of the landscape that is used in conjunction with GIS or remotely sensed imagery. The function of a DTM is both to represent the features of the landscape accurately and to be a useful tool for analysis of the terrain. The key to a DTM is to properly represent a Z value for X and Y locations. With a Z value, the model can be shown on a perspective view to demonstrate the appearance of the terrain. But this doesn't necessarily make it a 3-dimensional model. In fact, a DTM is usually best described as a 2.5-dimensional model. In a 2D model, all coordinates are measured with X and Y values without a number for Z at these coordinates. In a 2.5-dimensional model, a single Z value can be assigned to each X, Y coordinate as a measure of elevation at that location. In a full 3-dimensional model, multiple Z values can be assigned to each XY coordinate. Often, a DTM has one elevation value measured for the terrain height at each location, making it a 2.5-dimension model. A triangular irregular network, or TIN, is a way of storing continuous surfaces. It is vector-based and works in such a way that connects known data points with straight lines to create triangles, often called facets. These facets are planes that have the same slope and aspect over the facet. Collectively, these hypothetical lines form a network covering the whole surface. TINs are efficient when storing heterogeneous surfaces, since homogeneous areas are stored using few data points, while areas with more variability are stored in detail using a larger number of data points. In other words, a TIN can be more detailed where the surface is complex by using smaller facets, and less detailed where the surface is more homogeneous using larger facets. TINs also have a high modeling potential, for example, in topography and hydrology. However, the unique way of storing data in a TIN often makes it difficult to combine with other spatial data formats. Instead, the TIN data would usually be converted to other suitable formats. LiDAR uses a laser beam to measure the terrain. In LiDAR, a plane is equipped with a system that fires a series of laser beams at the ground. The laser beams are reflected from the ground back to the plane, and based on the distance from the plane to targets on the ground, the elevation of the landscape can be determined. Height computation using LiDAR works like this. The LiDAR instrument on board an aircraft fires a laser beam at the ground surface below. Travel time of that laser beam is multiplied by the speed of light. This result is divided by 2 to find the distance between the plane and the ground. Then, if this distance is subtracted from the plane's flying altitude, the height of the ground surface can be calculated. For instance, if a plane is flying at 3,500 feet and a single laser beam is fired to the ground and returns to the LiDAR device, the distance between the plane and the ground is measured at 2,000 feet. By subtracting this distance from the flying height of the plane, we find that the actual elevation of the ground is 1,500 feet. The data collected by LiDAR is often referred to as point cloud data due to the high volume of point locations measured. After the data is collected and processed, the end result of the LiDAR mission is a highly accurate set of XY locations with a Z value. LiDAR points can also measure the heights of features such as tree canopies or roofs of buildings and can be used to create realistic-looking 3D models of these objects on Earth's surface. These digital surface models can be developed using LiDAR to measure the heights of all types of things on Earth's surface, not just the ground. Points labeled with a standardized description or classification. Classification is a post-processing setup performed by LiDAR providers. The heights of objects like trees or buildings are removed to create an elevation model of Earth's surface, such as LiDAR has become a very versatile remote sensing tool that is used extensively in both the government and private sector fields. DTM is used for the terrain with no buildings, and DSM is the actual representation. Laser pulses emitted from a LiDAR system reflect from objects both on and above the ground surface, vegetation, buildings, bridges, and so on. One emitted laser pulse can return to the LiDAR sensor as one or many returns. Any emitted laser pulse that encounters multiple reflection surfaces as it travels towards the ground is split into as many returns as there are reflective surfaces. The first returned laser pulse is the most significant return and will be associated with the highest feature on the landscape, like a treetop or the building or the top of a building. The first return can also represent the ground, in which case only one return will be detected by the LiDAR system. Multiple returns are capable of detecting the elevations of several objects within the laser footprint of the outgoing laser pulse. The intermediate returns in general are used for vegetation structure, and the last return for bare earth terrain models. The last return will always be from a ground return. For example, consider a case where a pulse hits a thick branch on its way to the ground and the pulse does not actually reach the ground. In this case, the last return is not from the ground, but from the branch that reflected the entire laser pulse. Mobile terrestrial LiDAR is captured from the ground using a vehicle or person with a handheld device on the ground. Data can be collected from anywhere the sensor can travel, including inside tunnels and buildings. It has many practical and specific industry applications, such as transportation, but can also create an immersive sense of place. This video is featured in the ArcGIS book, 2nd edition, found online at thearcgisbook.com. So, on to applications of digital terrain models. DTMs are used in geospatial technology for creating viewsheds, maps that show what can be seen or not seen from a particular vantage point. A viewshed is used for determining a person's visibility, that is, how far the person can see, from a location before his or her view is blocked by the terrain. A viewshed can be created by selecting a vantage point and then computing how far a person's line of sight extends in all directions until something blocks the view. Slope represents the change in elevation at a location by calculating the rise over run. When a slope surface is created from a DTM, information can be derived not just about heights, but also about the steepness or flatness of areas. Similarly, slope aspects can be computed to show the direction that the slope is facing for each location. This means that not only do you have information about where the steepest slopes are located, you also know whether they are north facing, east facing, and so on. Like any other map, it can be displayed with various color ramps to show the differences in elevations, but there are several ways to make the terrain model look more realistic. Hillshade models show the terrain, how the terrain would look under different lighting conditions. When you're constructing a hillshade, you can calculate where the light source will be located at different times with respect to the terrain and simulate the effects of shadows cast on the landscape by the various terrain features. By setting two parameters for the sun, you can determine different appearances of the terrain at different times of day. The first parameter is the sun altitude, a value between 0 and 90 representing the angle of the sun in the sky between 0 degrees and 90 degrees. Second parameter is the sun azimuth, a value between 0 and 360 that shows where its rays are coming from. The value represents a circle around the landscape, with 0 being due north, 90 being due east, 180 being due south, and 270 being due west. If you set values for sun altitude and sun azimuth, the terrain can take on various appearances to simulate how the landscape looks at different times and in different conditions during the day. 3D modeling for geospatial applications refers to the design of spatial data in three-dimensional form. Designing a 3D version of the buildings in a city's downtown district or a 3D version of the Eiffel Tower would be examples of 3D modeling for geospatial data. Like all of our other spatial data, the 3D models would be georeferenced to take advantage of real-world coordinate systems and measurements. Thus, each item will be modeling will have proper geospatial X and Y coordinates, but because we'll be working for a third dimension, there will be a Z value assigned as well to represent the height of the object above whatever surface it's measured on. Digital terrain models aren't just limited to flat images on a computer screen or a proper map. Remember that constructs like DTMs are 2.5-dimensional models, and because such a model that has a Z value, that Z value can be visualized in a 3D view. It is accurate to say that these types of visualizations are really pseudo 3D views because they're really 2.5-dimensional and are not really full 3D models. Setting up a pseudo 3D view of a digital terrain model involves examining it from a perspective view. Points or raster cells are elevated to the height of their Z value, and the resultant model is shown from an angular view. In this way, mountain peaks can seem jutting up from the surface, and a meteor crater can look like a depression into the ground. In many geospatial technological applications, the model is interactive, allowing the user to move or fly over the terrain, skimming over the surface and banking past mountains. Beyond viewing the terrain in perspective view, there are numerous ways of artificially altering the appearance of the terrain to make it more realistic looking. One way is to drape imagery over the surface. Some advantages of 3D and geospatial technology. So vertical information. This would be the most obvious advantage of a scene is its ability to incorporate vertical information, the surface elevation of mountains, the surrounding landscape, the shapes of buildings, or the flight paths of jetliners. It's the power of the Z. A campus 3D viewer is the ideal way to navigate around large grounds and also within the building. This visualization of the Esri campus in Redlands, California allows us to visualize the campus in 3D, see selected indoor points of interest, as well as route to your desired destination. Intuitive symbology in 3D, the extra dimensions enables you to include more readily recognized symbols to make your maps more intuitive. You are able to see all the data from all viewpoints in situ. Every symbol that you recognize on a map saves you the effort of referring to the legend to make sure you understand what it shows. Showing real-world bird's-eye views, many of man's earliest maps, particularly of cities and smaller human habitations, were portrayed as scenes. These stylized maps were created as static 3D bird's eye views and were successful in providing understanding of a place. Today's GIS authors interact with and see the scenes from many perspectives. For example, let's consider point cloud data gathered from LiDAR. Each point is recorded with its real-world X and Y coordinate, but also the Z value of the height of the surface or object on top of the surface at that point. In GIS, you can display those points by placing them at their actual height above the surface to reconstruct a 3D representation of the surface or features being measured. With a dense enough point cloud, you'll be able to start seeing the dimensions of the features begin to take shape and give a 3D representation of the area. If points can be given a Z value and shown that at their height in GIS, the same can be done with other objects. Also, rather than just placing a point at the height of an assigned Z value, you could place a point on the ground and stretch it up to that Z value height to create a pole rather than a point. Similarly, you could extend a polygon representing the outline or footprint of the backyard shed up to the height of a Z value to create a block-like appearance instead of a flat polygon. Extending an object to the assigned height of the Z value is referred to as extrusion. Applying imagery to buildings or other features can transform blank 3D geometries into realistic-looking, detailed 3D models. Pasting aerial and low-angle oblique imagery to individual buildings' faces can be done in one of two ways, realistically or procedurally. Realistic textures are generated from aerial or oblique images captured for the actual building or feature that is being modeled in 3D. Every surface of the building has a unique texture that represents what each individual facade or roof surface looks like in real life. This approach typically involves higher data acquisition costs and labor, but creates a very realistic 3D scene. For example, familiar or iconic buildings look as they should, with all the correct architectural details. Procedural texturing involves the application of a geotypical or architecturally typical facade and roof textures onto 3D building forms. These textures can be applied to existing untextured 3D building models, or they can be applied as part of the procedural modeling process of converting 2D footprints into textured 3D buildings. Procedural textures are applied according to rules that determine the type of texture for each building and how many times it is repeated. These textures are typically collected from oblique or street level images, which are then rectified and edited so they can be repeated seamlessly around the perimeter of each building or floor. It creates the most realistic looking 3D buildings. Texture libraries are grouped and can be applied to match the land use type of building, its height, the number of floors, and the regional architectural style. Often, texture libraries are split into two groups: the ground floor, which is usually taller and may contain entrance doors and store frontages, and the upper floors, which repeat uniformly. While the textures on a procedurally textured building may not exactly match their real-life counterparts, they are inexpensive to generate and closely approximate the look and feel of different general building styles. Procedural buildings are also very useful in urban planning, where the heights and styles of proposed buildings can be changed easily to evaluate different scenarios. If points can be given a z-value and shown at their height in GIS, the same can be done with other objects. Rather than just placing a point at the height of an assigned z-value, you could place a point on the ground and stretch it up to that z-value height to create a pole rather than a point. Similarly, you could extend a polygon representing the outline or footprint of a backyard shed up to the height of a z-value to create a block-like appearance instead of a flat polygon. Extending an object to the assigned height of a z-value is referred to as an extrusion. Keep in mind that these items extrude from ground level up, and some objects can't be designed this way. For example, suppose you want to design a 3D model of a 10-foot high pedestrian walkway that's 15 feet over a busy road. If you digitize the bridge's footprint and extrude it to 10 feet, it will look like a wall blocking the road rather than a bridge over it. To get around this, you have to apply an offset or a z-value where the initial object is placed before you do the extrusion. In this case, the digitized polygon representing the bridge will have to be offset to a height of 15 feet, and then it will have to be extruded to a height of 10 feet. "3D visualizations can be easily published and viewed just using a web browser. Cesium is a free JavaScript API that can be used for designing 3D web applications. The open source Cesium can be used for rendering geospatial data on a 3D virtual globe and accessing it through a web browser. How does the addition of visualizing these kinds of geospatial data on a 3D virtual globe in your browser aid in interpreting the data or communicating the concept to the viewer? Making a handful of realistic looking buildings and trees is relatively easy. By trying to design all the structures in a park, or an industrial area, or a college campus would take a very long time to design each item or building by hand. And just imagine trying to design tens of thousands of buildings for an entire city by digitizing and extruding each set of polygons, adding textures, doing additional design using 3D software, then populating it with trees and objects. Doing all this for each individual building would take an extraordinarily long time. Stereo images show two images rendered apart from each other. When you look at something, your eyes are seeing the same thing from two slightly different points of view, which is why you see depth and distance. Stereo images use a similar principle. They are two representations of the same thing taken from two slightly different positions of the camera or sensor. Remote sensing has made use of stereo imagery for measuring the heights and depths of areas. Overlapping aerial photography from planes and drones and images acquired from satellite sensors can be used for creating stereo data. Software such as the popular Pix4D program can take UAS photos and search for thousands of common points between the multiple overlapping photographs. Pix4D then uses that information to create a 3D point cloud of these common locations. Using that, the imagery from the UAS can then be knitted together to form a mosaic and then displayed in 3D. In this way, heavily overlapping imagery and modern photogrammetric techniques can be used to calculate the heights of locations in an image and to view the remote sensing imagery of a large area in 3D. Obtaining the same type of imagery for an entire city can be done by flying a plane over an area and collecting high-resolution aerial photography from multiple angles. Once again, by using the amount of overlap, the imagery can be processed to find the same locations in the images and photogrammetrically calculate the distance from the ground to the camera and thus the heights and dimensions of those places. This information can be used to create a 3D mesh model of the places on the ground below the plane. Think of it as a simplified outline of the structures and landscape on the ground. Some systems also incorporate LiDAR point cloud data collection into the mix for better rendering and more accurate or detailed 3D mesh models. Then the imagery captured by the aerial photography from the sides of the buildings can be applied to the mesh model like a texture. Virtual reality also represents an interactive and immersive digital environment in which 3D visualizations of geospatial data can be utilized. VR simulates the visual presence within a computer-generated world. With geospatial data, this takes the form of viewing 3D models in a VR headset, which projects two images for stereo viewing. Also, a VR headset blocks out your vision from the areas other than the projected images in the headset and keeps the imagery in front of you at all times. One of these is augmented reality, which adds new interactive digital elements to the normal view of the world around you. The goal of augmented reality is to show you the real world, but with computer-generated objects superimposed onto your view of it. Augmented reality is also named because it artificially enhances what you would normally see with computer-created content. An example of an augmented reality application is the popular Pokemon Go mobile game. Pokemon Go uses your phone's camera to show you a view of what is really there in the real world, but with a cartoon monster and game items superimposed on this view. You can use the app to interact with these computer-generated elements as a video game. The kinds of technologies described here for video game elements can be used for a number of other applications using real-world geospatial data. Mixed reality is similar to augmented reality in that it creates digital overlays onto your view, but connects with these interactive computer-generated items to real-world locations, allowing you to interact with both real and digital content. If you wear a mixed reality headset such as the Microsoft HoloLens, geospatial data can be overlaid onto your view of the real world locations, and you can interact spatially with these items. Imagine picking your next vacation destination by just scrolling through the planet. Well, now it's possible with Spatial Earth, a new app by Adio that brings Google Earth to your living room with Apple Vision Pro. This app invites you on a captivating journey across the globe from the comfort of your home, powered by photorealistic map tiles. Spatial Earth offers an immersive exploration experience, allowing you to navigate through the entire globe, including vast landscapes over 2,300 cities and natural wonders in stunning 3D. Whether you're a curious explorer, a student eager to learn, or simply looking to experience the world from a new perspective, Spatial Earth is your getaway to discovering the planet's breathtaking diversity and beauty. And then last but not least, we have building video games with ArcGIS technology. This is an article that was published by an RIT professor, Brian Tomaszowski, and a couple of others. It is a good read. I do recommend it. And then I will actually be going a little bit more in depth with the video game side of GIS next week as an optional lecture, and there might be a few extra credit questions about it on the final quiz. So with that said, that is all I have for the lecture. This is our second to last lecture. Like I said, next week is optional, so if you don't feel like watching it, then I hope you enjoyed the course, and there will be a last couple things. You obviously have your final project that is due in a couple of weeks. There will be one more quiz and one more homework assignment. Homework assignment will be up with this lecture, so check it out. And then the last quiz will go up next week, and you'll have about a week to do it. So with that said, as always, if you have any questions or concerns, please reach out to me, and I will see you guys next week.